Since all living systems that we know of operate in an aqueous environment, our first task as biochemists must be to understand the nature of what is actually a rather exotic substance. What are its properties and chemical propensities? Then we can start to look at biological molecules and how they function within this environment. Let's first review the principles of electronegativity and bonding, and then see how these relate to water. Electronegativity is the force of an atom's attraction for the electrons that are shared within a chemical bond. From the table pictured here, we can see that oxygen and nitrogen are more electronegative than carbon and hydrogen. This means that the distribution of electrons within a bond between, say, carbon and oxygen will be closer to the oxygen atom. This property of electronegativity often relates to chemical reactivity as nucleophiles or electrophiles. Because electronegativity exists, there are polar bonds that result from an unequal sharing of electrons. The more electronegative atom within the bond would have a greater attraction for the electrons and would therefore carry a more negative charge, though not an actual net charge. This generates what is referred to as a partial dipole. Water is certainly a good example of a molecule containing polar bonds. The negative dipole associated with the oxygen atom and the hydrogens each carry a positive dipole. The measure of the polarity of a chemical bond is called the dipole moment. You can think of it as though the molecule were a magnet and the dipole moment is a measure of the strength of the magnet. The dipole moment is often illustrated with an arrow which points to the center of electronegativity. Notice that in the case of water, the arrow points toward the oxygen atom. To better understand this subject, let's consider the van der Waals radius, which is the distance from the nucleus of the atom to its effective electronic surface. If we think of each atom as a magnet, the van der Waals radius is the limit of the magnet's ability to attract. In any type of bond formed between atoms, there must be an overlap of their van der Waals radii, else they can have no influence on each other. Note that the greater the overlap, the shorter the bond distance and the stronger the bond. From the illustration here, you can see that covalent bonds are much stronger than hydrogen bonds because there is greater overlap of the van der Waals radii. We want now to consider the difference between a polar bond and a polar molecule. A case in point is CO2, carbon dioxide. Because of the difference in polarity between oxygen and carbon, the bond between them is certainly polar. However, because the alignment of the atoms is linear and symmetrical, the two oxygen atoms pulling in opposite directions with equal force, the net effect on the molecule is to make it nonpolar. Another common type of intermolecular force is that of ionic bonds, resulting from the attraction of opposite charges. This is what holds sodium chloride crystals together. We find a similar type of charge-charge interaction or electrostatic attraction between functional groups that carry opposite charges. In the upper right, the figure demonstrates that a positively charged amine group forms what is called a salt bridge with a negatively charged carboxyl group. When potassium chloride is dissolved in water, water molecules surround the ions in what is referred to as ion-dipole interactions. The positively charged potassium ions interact with the negative dipoles on oxygen, and the negatively charged chloride ions interact with the positive dipoles on the hydrogens. We'll look at some other types of non-covalent bonds in our next lesson.